this sigil symbol. Which I recently proved. And so the first theorem is the one that Europe mentioned in his talk. And hopefully I will also have time to go to the second and third theorems. So let me first fix all these parameters. So similar to Europe's talk, we have this Q parameter. Q parameter is, and the Q theta is the inverse. And then we have so then there are some other parameters which is used in the probabilistic setting of Liouville CFT, and I will also mention it. So one of the unfortunate things is that if you have two communities work on the same topic, they tend to use different notations, and it takes people like more than 1 year to figure out how to match. It definitely took me more than 1 year. So this. Okay, so we also have this gamma equal to V, and also so okay, and also in my talk, the alpha in Jürgen's talk will be my A. So I have a parameter A belongs to Q. This is a spectrum. So my A is U alpha, and my alpha is 2A. Alpha is 2A, which sometimes they also be labeled by Q plus IP. And the A belongs to this range. Is if and only if P is positive. Okay. And then we also have this conformal dimension. Now it's going to be this. This is the same as in Jürgen's talk. And okay, these are all the parameters. And now, okay, so the first part of my talk will be, I will just introduce the concrete definition of this thing as a special function. And then I will explain the link to this quantum. So in order to define this function, I need to first introduce this so-called double sign function. So the double sign function is a meromorphic function specified by two shift equations. So it is a solution of this shift equation. It's the unique solution to this with meromorphic function, and so it also equals to the ratio between the bounds double gamma functions. And these bounds double gamma functions, they also appear in the expression for the DUZZ. Okay, so now let me define this sigil symbol. So it depends on 6 parameters, 6 variables, and of course it also depends on this B. So I will have some new variables q and t, there will be some linear combination of these a's. I will first write down this expression and then write down definition q and t. So gamma is a contour, and I will specify it afterwards. And here, at this moment, these definition of T's are just some random linear combination of these A's. But I will draw a picture to demonstrate what they mean. So here, Q4 is just a fixed number, and I'm only defining it to make this formula more beautiful. So the real variables are these T's and Q's. And so the way to see this is to the way to think of these T and Q's is we draw some tetrahedra. Okay, and then we label the edges. And then we can see that all the T variables, they correspond to faces. So these different T's are just you summing over all the edges, edge variables on every face. Okay. And then these Q variables, they correspond to diagonal edge pair. In the sense that every Q just corresponding to, we first choose a pair of diagonal edges, and then when we sum over all the A's, we don't sum over that pair. Is this clear? Okay, so with this interpretation, it's easy to see that so this function, has tetrahedral symmetry. And so the most important property of the signature symbols is the pentagon relation. And in this talk, I will give 3 different ways to think of this pentagon relation. So the first way is through this point of view of topological quantum field theory. So since this signature symbol has tetrahedral symmetry, we can think of it as assigning some weight on certain tetrahedrals. And then we can try to assign a certain partition function to triangulations in 3 dimensions. And this is a so-called Turaev-Viron partition function.
This 6a's, are they just any real numbers or positive real numbers?
These A belong to the spectrum, belong to this Q over 2 plus IR. These A's.
Ah, like literally, okay.
Okay, so this guy as a function, it is a meromorphic function. But for my talk, I only focus on the spectrum. This is where you have a connection to quantum group. So I need to find the view. Okay, so the definition is very simple. So let's say the particular function of a single tetrahedron is so let me just let me first or maybe I should say particular function weight. Okay, so let me first introduce this notation. So I will use this to write these signature symbols. So suppose I have a triangulation with edge labeling E1 to E6, then the so I can use this symbol. Okay. So now let's consider these kind of triangulations. So this is just the gluing of two tetrahedrons, okay? And then, so I define the partition function of this guy. So I define the partition function of this guy to be, so this is just saying that for every tetrahedron, I just consider the corresponding signature symbol and then multiply them. And this is, so this applies to all the triangulations where we do not have internal edges. So we only have external edges. Then this guy will be a function of these variables on external edges. And then the second case is suppose we have some inner edges. So I still have the same tetrahedron. Okay, so this is the same as this picture. Now let me draw another diagonal edge. Draw this vertical edge between the two, between the top and bottom points. Then after I draw this edge, this becomes a gluing of three tetrahedrons, and there's one internal edge. And then for these kind of scenarios, the definition of this is given by so we first need to integrate over all the internal edges. So what I'm doing here is that I'm still just multiplying all the weights for these tetrahedrons. And then whenever I have an inner edge, I also integrate over some spectral measure. And this measure is given by this. And this is actually the Planck measure for this corresponding quantum group. Okay, and then the Polygon relation of the signature symbol just says that these two, you call it these two particular functions are the same. And from this, we can see that this actually gives you a way of defining some topological invariant, which is called the Turaev-Viron invariant in literature. And so as we can see, this signature symbol is a super complicated function. So even this function SP is super complicated. And now you have like 16 SPs timing multiply together, and then you do some integral. Oh, I think I forgot to specify my contour there. Just so this contour here. So the gamma is any contour in any vertical line between crossing. Yes. So my point is that this is a super complicated function, and then this means that this is a very non-trivial identity, and this is the identity first proved by Ponsot and Teschner using the perspective quantum group. So I think I believe that a big portion of the audience knows what is the signature symbol of the tensor category, but also maybe there's a portion who don't know. So let me just explain the definition of the signature symbol. So I will use the example of the SU2 to demonstrate the definition of signature symbol. SU2. So we consider all the unitary representations of SU2, and they form some tensor category. And then, okay, so maybe I label these representations by V1 and V2. And then we know that, for example, V1 plus V1 tensor V2 equals to this guy. It can be decomposed into these very useful representations. And then there is so we have these maps that embed VS into this V1. And all of this kind of maps, I can write it as the homeomorphism of G invariants. And this space has dimension 1. Meaning that all these multiplications here are just 1. Okay, now we can also consider this space. We can consider the space of all these mappings from V4 to these 3 tensors. So then there are two natural bases for this linear space. Depends on how whether we first fuse V1 V2 or we first fuse V2 and V3. Let's say we first fuse V1 V2, and then one natural thing to do is we first choose the S so that we first embed the V4 into VS tensor V3, and then we embed the VS into V1. And we can use the following diagram to write this. So this is the thing that I first embed before using some VS tensor V3, and then I embed this VS into V1 tensor. So this is one way of labeling the base of this space. And then I have another use this. So another natural base is we first okay, so we can have like V2 times V3 equals to some other decomposition. Then what we can do is we can embed V2. And this can be written as this. Okay. So now we have two bases of this space, form G from V4 to V1 tensor, V2 tensor, V3, and then there should be a changeable base. And the secret symbol is the changeable base. Okay, so according to in my notation, never mind. Okay, and this is the definition of the secret symbol for SU2. And okay, so and then
this depends on the short. You choose a certain embedding of the.
Yeah. So this depends on the normalization. So it depends on how you normalize.
So if you change this, then you get some scalars.
Right. Yeah. And my claim is that under certain normalization, this B secret symbol I just erased is the secret symbol for this modular double of this UKSL2R thing. But maybe let me elaborate on this. So this is the secret symbol for SU2, and you can imagine that for any compact group, you can define the same similar thing. And then you can also do the same thing for the principal series of SL2R. Can also define. For the principal series. Unit representation. Okay. And the difference is that you need to replace the summation into an integral. But this is something different. And then, I will not give a definition of quantum group, but quantum group is a way of deforming the tensor algebraic structure of the D group and D algebra. So it will simply, so you can also define tensor structure, including secret symbol. for these quantum groups. Okay, then I will not give the definition of these groups, but you can imagine that there should be some natural wave deforming these the algebras. So maybe I still keep this definitions. Okay, so now it is a, so the modular double this equals to the tensor of the two quantum group. And this is, I think, is first introduced by Fadiev. And the theorem by Ponsot and Teschner around the 2000 is that so previously defined secret. The previously defined function, I have a notation for that function. So notation is this. To be more precise, in the original paper by Ponsot and Teschner, the expression of the secret symbol is a little bit different from what I wrote here. It does not have the tetrahedral symmetry. The one which has a tetrahedral symmetry uses another normalization, and that was first introduced by Teschner and Wattenhoff. One is tetrahedral symmetry. Okay, so now okay, so now it comes to our first theorem. So the theorem is that this fusion kernel exists. The fusion kernel mentioned in your talk exists. Equals to the secret symbol. After some normalization. Involving DUZZ. This is just the same statement as what you wrote in his lecture. And along the way, we also prove that the conformal block is convergent power series. Oh, I think one thing I forgot to mention is how to see the Pentagon relation from the quantum group point of view. Maybe I first explain that, and then I say some ideas about how the proof goes. So we can see that the fusion kernel is a changeable base between this diagram, right? And then in order to see the Pentagon relation, we just need to consider the same thing, but with 5 modules. So now we consider this space. We also consider all the intertwiner from this. Then there are 5 different ways of grouping these modules to find the base. And these 5 different ways, they can be related by these fusion kernels. And this Pentagon relation is exactly the how you transform. So let me just draw the picture. So this is one. This is one way, and this is a so-called Pentagon relation. It's also the namesake. So you can imagine that I have a different secret symbol to flip between these different bases. Okay, so now let me, so how much time do I have? So when I started, I don't remember.
Yeah, you have more, at least 20 minutes.
At least 20 minutes.
Yes.
Okay.
Can I ask a question? Sorry if it's a basic question. Naively, in your diagrams, there are 7 symbols because there are 2 internal symbols, no?
What do you mean by, I think, okay, so here, this is only to capture the flip between this part and this part, and this is fixed.
I see there are 5 external
So the order of these 5 graphs are not arbitrary. So you have to go between between 2 neighbors, you only have 1 flip.
Yes, but you have 2 internal symbols to.
Yeah, but there are 2 internal symbols. But when you flip from here to here, this one is fixed.
Okay.
Yeah. And then this is saying that if I go from here to here, there are 2 different ways. One way is go from here to here. The other way is go from here to here. And this corresponding to exactly these 2 different ways of writing the.
Thank you very much.
Can I ask a question? Sorry. In your theorem, by saying that the fusion kernel exists, it means it also implies some kind of uniqueness.
Okay, so I mean, we didn't prove uniqueness. What we showed is that if you, okay, so if you plug in this concrete function into this formula that you wrote in the last lecture, this like this S channel block equal to this integral times the T channel block, this identity holds. This is identity. And I think it is unique also.
Yeah, so, but don't you also prove that there exists this expansion of one set of conformal blocks into the other?
Yeah, yeah.
In some sense, this defines the kernel uniquely by relation, right?
And it definitely defines the kernel. Yeah. I think okay. So I will mention that. Okay. So later I will also comment on the physical argument about how he argued this fusion kernel. He has a very solid argument. If you assume the fusion kernel exists, then there are some solid arguments to say that this fusion kernel has to be this function. But showing a priori the fusion kernel exists is not true. Because you have two very different set of power series. Okay, so the proof is based on the probabilistic Liouville CFT, and I realized that I'm the first one to speak about Liouville CFT. So let me first give some like probabilistic definitions of these correlation functions. Okay, so the Liouville CFT, formally it is defined by the following path integral. So this is the correlation function. So this is given by this integral. Okay, so I'm talking about this correlation function on the sphere. And this thing with the a priori it would depends on a metric on this sphere. So G is a metric on this sphere. So and this is the Liouville action. So this is why my alpha is Europe 2a, because in the physics literature, when people write these things, sometimes they write e to the 2 alpha times phi, which I didn't appreciate fully, but at least there seems to be some convenience in doing that. In probability, we just use this alpha. And this Liouville functional. Okay, so this Liouville functional, it also depends on Q. Yeah, Q is there. So, so I will write it into two parts. So one part is the free field. This is the free field part. So I will use a new notation for this. So I will call this the action for the Gaussian free field is background charge Q, and this is the background charge. And So this is a Liouville potential, and this nu is a positive thing. This is a cosmological constant. So, and the probabilistic definition of this coordinate function is can be done into 2 steps. So step 1, it's not very hard to make sense of this measure. So this is the random field measure corresponding to the Gaussian free field with background charge Q. And this is something that if you know how to define Gaussian free field, then it's easy to add some linear shift to the Gaussian. So this is still a Gaussian measure. Yeah. This is a Gaussian measure. It's a Gaussian measure on fields. Okay, so this is step 1. Okay, then okay, so once we have this measure, let's denote the expectation over this measure by this. I have this alphas, I have Q. So given any test function f, I can consider the average over this measure. It's just some Gaussian measure. Okay, and then in order to define this guy, so we just need to say that the second step, just to say that it's a Liouville coordinate function. Equals to this average over e to the mu. We're just saying that we choose a very special f, which is this function. Okay, and then the whole difficulty is how do we make sense of this one variable? Because since this is a GFF measure, this is not a well-defined function. It's in 2 dimensions, it's only a generalized function. And for generalized function, you need to some additional care in order to define this area measure. And this is using this thing called the Gaussian multiplicative calculus. Gaussian multiplicative calculus is a way of defining this one. And so the theory of Gaussian multiplicative calculus tells you that gamma between 0 and 2 is a sufficient and necessary condition for this procedure to have a non-trivial limit. Okay, so this gives the definition of this coordinate function. Then okay, although Europe already wrote this theorems, so let me still recall the DOZZ formula and the conformal bootstrap for this Liouville collision functions. So maybe I can remove this. So the correlation function have this basic property. So suppose psi is a Mobius map. Then this will just be equal to, there will be some factors. And the factors are given by the conformal dimension. And this means that the 3-point function have the following form. So it can be written in the following form. So we have a constant depends on alpha 1, alpha 2, alpha 3, and then this is a z dependence. Here.
With minus sign.
Oh, there's one. Okay, cool. I was wondering like whether it's a plus or minus. And then a theorem due to Compagnon-Rosmanas is that this guy. So remember that this is a probabilistically defined object. This is the expectation of certain average here. It's an expectation of certain Gaussian manipulated locales. And the theorem is that this equals to the DOZZ formula. This is some concrete formula proposed by DOZZ, which involves the ratios of a double gamma function. Okay, so I have 5 minutes left, and now I need to state my last 2 theorems and also the proofs about the Ponsot and Teschner. So I will see how much message I can convey during these 5 minutes. First of all, so we can also consider so the proof Oh, maybe I should also, okay, so there's this theorem, there's also another theorem by Colin and it's like a conformal bootstrap. For again, this is a identity. On the left-hand side, it's just the probabilistically defined correlation functions. On the right-hand side, it is the integral over, it is the integral of conformal block to the square integrated over this measure defined using product uses z. So this is the, so one nice thing about this is that if you look at this definition, this definition, so in the proof of the conformal bootstrap formula, it doesn't matter whether you first fuse V1, V2 or you first fuse V2, V3. And just the fact that you can define this Liouville correlation function and you can prove the conformal bootstrap tells you that crossing symmetry holds for the DUZ formula along the Liouville spectrum. And then probably, and as you mentioned, so one of his motivation to propose this fusion kernel and unitarity is to say that the conformal block, the DUZ formula indeed provides the crossing symmetric solution to this theory. And I think so. One of the, I think so. So one interesting question is that it is believed that this crossing symmetry should also hold for the central charge smaller than 25. I think so. Actually, is that for C not in this range. And this is something not proved.
But by that you mean that, because we know that in general for complex central charts, the DUZ is not a unique solution to some shift relations.
Yes, it's. I mean, I think okay. So DUZ is a unique solution, is a unique meromorphic function satisfying certain.
Right, but when the central charts between 1 and 25, the B is complex, so there is an overall elliptic function that you can multiply your DUZ formula with. Still
yeah. So okay, so
maybe
okay, so let me not talk about the uniqueness. I'm just saying that the conjecture is that this provides a solution to the crossing equation, and this should give a definition of Liouville for C for central charge not in this range. But the difficulty is that we don't even know how to prove convergence of conformal block in those cases. Okay, and then okay, so now let me state my second theorem. So the second theorem is also concerning this this secret symbol. So in this Liouville theory, you can also define the boundary correlation functions. The boundary correlation function is, let's consider the upper half plane. You can imagine that I have these boundary marked points. And then there's a similar definition of the correlation function, which have both the block insertion and the boundary insertions. And the second term is that, so if you consider these, so these boundary correlation functions, so they are given by these secret symbols. This is another conjecture proposed by Ponsot and Teschner. And here, so this, so beta 1, beta 2, beta 3 is just the insertion at these points. And this sigma 1, sigma 2, sigma 3 is a certain labeling of the boundary condition. So you have this boundary condition, sigma 1, sigma 2, sigma 3. Okay. And so the way we prove, okay, so the reason that Ponsot and Teschner made this conjecture is to draw the analog between Liouville theory and A-series minimal models. So for the rational CFTs, it's kind of known that the boundary solver constant and the diffusion kernel should be related. And the reason is because the boundary crossing symmetry is the same as Pandion relation. So, given the fusion kernel equals Cj, so the philosophy is that if you know that fusion kernel equals the secret symbol, then the Pandion relation satisfied by the secret symbol is exactly the crossing symmetry for the boundary bootstrap, for the 4-point disk boundary bootstrap. And then if you somehow believe that crossing equation give you some unique solution, then this would be a natural guess. And I think this was I think so when I wrote the paper, he mentioned that he was inspired by the work of Racah-Wigner, A-series models. And then, so the way we prove theorem 1 is that we first prove theorem 2. So we first use the idea of proving the DUZ formula combined with some other ideas, which is called the mating trees. It is another branch of probabilistic Liouville theory, which is related to how the Liouville theory is interacting with Schramm-Lorentz evolution. So combining with the DUZD proof, together with some input from this SLE LQG coupling, we can first prove theorem 2. And then after you have theorem 2, you can reverse the logic to get to this. So basically, you can first start with the boundary crossing symmetry, and then you use the unitarity of the secret symbol to deduce that the fusion equal to secret. And along the way, we also prove that along the Liouville spectrum, these conformal blocks are convergent power series. Okay, and okay, I'll just quickly mention theorem 3, and so on next Wednesday, Baojing will give a talk on this theorem. So theorem 3 says that the Turaev-Viron invariant satisfies volume conjecture for 3 manifolds with So for people who know volume conjecture, you will know what I'm talking about. For people who don't know, I don't have time to explain. But on next Wednesday, Baojing will give a talk about it. Thanks.
So we have time for 1/2 questions. Well, maybe coming back to the point about this continuation to C smaller than 25. So I think you mentioned briefly, but I would like to hear it more precisely. So the difficulty that you see is with the conformal blocks, yeah? So if the standing assumption that sort of the conformal blocks are meromorphic in the conformal dimensions, if this would hold, then I think it should just continue, right?
Okay, so basically, okay, so far using Liouville theory techniques, we cannot vary the central charge. So we have to fix the central charge. But here we need to, so if you want to say something like this, you would need to do some analytic continuation of the central charge. And this so far we don't have tools yet.
Yeah, but okay. I mean, you said you have the absolute convergence of the conformal block series.
That's true. Okay, so
That is
yeah.
true, right? I mean, the coefficients are rational
think
in central
okay,
charge
so-
and dimension. So if this is absolutely convergent, you would
but,
conclude
okay, so
that sort of the
let's see. So I have a convergent power series. Let's say A and C, Zn. So this is a convergent power series, and this A and C is some like a rational function in the central charge. Let's see. But then you cannot just conclude that this convergent series as a function of C is also a meromorphic function. This does not hold automatically. You need some like a uniform convergence or whatever. It's like you need some uniform bound on this, which we don't have. And yeah, so at least if my complex analysis is not too bad, I think you cannot conclude that. Yeah, just the convergence of this can be meromorphism C. So the key thing is we have to fix C between like, which is B between 0 and 1.
But okay, but the precise statement is we don't know, but it could well be that the thing
Of
is
course,
as sort of was conjectured by
I mean,
topologists for a long time that it is actually in the end also for fixed Z
Of course,
meromorphic in central charge.
Of course, I think that would be the conjecture. I mean, even for C between minus infinity to 1, it should be a convergent series, but we don't know how to prove it. One hope I'm having is that, for example, there are now like developments about conformal bootstrap for the conformal loop ensemble. And if this thing developed sufficiently maturely, maybe a lot of story here can be carried out there. Then maybe you can improve. But so far, it's only a dream now. But that's one of my motivation to understand this conformal bootstrap for the conformal loop ensembles.
In addition to the fusion kernel, there is another object called the modular kernel.
Yeah, that can also be done. So actually here in theorem 2, we also have a statement saying that if you have the bulk boundary correlator, the bulk boundary correlator will be equal to the model for 1-point torus. And also the 1-point torical conformal block is the model kernel also given by this boundary correlation.
And you prove the same thing for the modular kernel in your paper.
Okay, so one caveat is that the boundary bootstrap for the when the bulk cosmological constant is positive, the boundary bootstrap is only proved for the case gamma square is negative for some technical reason. So if we really just carry out this reasoning, then we would only get this fusion kernel for this smaller. But on the other hand, we can also implement the same philosophy if we set the boundary, if we set the bulk cosmological equal to 0. Then for the when the bulk cosmological constant equal to 0, the boundary bootstrap is proved for the full range. And then you can, by matching the two, you can conclude that the fusion kernel always equal to the series. This is a good one. Maybe I want to make a related remark, which is so we have a draft. We have a draft about this theorem back to 2022, and there are two reasons why this draft still has not become a preprint on archive. So one reason is that this boundary bootstrap paper is still being finished. So I think it's going to be finished soon, hopefully. So this is one reason, and the other reason is that the draft we had online. So when we write that paper, we don't understand the quantum group yet, and so our proof is only work for the probabilistic range. So our alpha values are not on the Liouville spectrum, and then thanks to the help of Audrey Wu, we now can prove things along the Liouville spectrum, which is the real interest if you want to connect it to modular tensor category and the quantum group as well, and the quantum Teschner. And this is why if you look at our online draft, we have 4 authors, but in that theorem we have 5 authors.
Okay, so I think that we can thank Xin again. And remember to take the ticket.
Non, c'était fermé. Et ce matin, je suis retourné, bah, ils n'avaient pas.
Tu as passé un sale quart d'heure.
Ouais, ça m'a fait très bien pour moi.
That's it.